As we said, we study a different vector product. So the first vector product, the scalar or dot product, you multiply as such two vectors together and you get a number. The vector product or the cross product, you multiply two vectors together and you get another vector. In next week's lectures, we'll see the applications of these two. So in a rough sense, the vector product describes the torque. Now we will explain this in time of two vectors. So if you've got vectors that have a large angle between them in the sense of close to 90 degrees, this is a kind of situation where these vectors can kind of produce a good torque. We will see this in time, whereas vectors like this will have a small vector product. So this, yeah, we'll explain this. We may as well explain this. These will have a small. Now, what does large mean? What does small mean in terms of magnitude? So if this is U and this is V, in this one, the magnitude of U cross V will be, the largest it can be is like the length of one by the length of the other. So this isn't describing the vector, that is the cross product. This is describing the length of the vector. It'll be approximately length of U by length of V. And for both of these two, say for both of these two, the magnitude of U cross V will be close to zero. So that's what I mean about it being a small vector product. Now, of course, the thing is, if the magnitudes of U and V are very, very big, if you have a very, very big force, you're going to still have a moment, even if it's not very efficient. But really what it means is that the length of U times V as a percentage kind of length of U by length of V is close to zero. Okay, so let's kind of put some sense on this if we can. Now, what might help me is if I put the V's somewhere else. I won't always be able to do that. Yeah, so I'm going to put the U on top of the V there. And God, it's kind of hard here, but so this is U, then this is V. This one, so this is U and this is V. I might have to edit this a little bit as we go, we'll see. So in what I'm actually thinking about is doors, okay? So in this one, V kind of represents the door. In this one, U kind of represents the door. And in this one, U represents the door. Okay, so they're like doors, maybe a bit better color. Now we will do all this properly because this should be a bit confusing the way I'm doing it. So then the tip of those is going to be a hinge. Fulcrum, well, let's just say the hinge of the door. That's a hinge. That's a hinge. That's a hinge. And then imagine the blue bits are forces. So this is a force. This is a force. And this yoke is a force. So the door is open, and this is someone now where the actual neutral of the door, maybe I'll just draw some random lines that represent that. So let's say there. So you imagine looking from above, there's the door, and then someone pulling the door shut. Okay, this one you're looking from above. We'll put the door over here. Yeah. And here, let's see where we put the door. Put the door from here. Okay. So here you can see that this force will close the door. It'll cause a moment. This force isn't very good at closing the door. Eventually, so this is basically really weird. So the door is kind of open, and rather than kind of pushing it at kind of right angles, you're pulling the door, and that's not really going to do much turning. in fact, it's just going to, if the door is slightly not in the direction that you're pulling it, if you pull it, you'll get a little bit of a moment, and then U and V will be parallel. Now this is a weird one. So this, I think, would actually close the door, but it's a really, really weird way of doing it because you're just kind of pulling against the handle. You're not going the right way. So really what you want is for there to be a large moment is that the angle between the vectors is large. This is basically what I'm saying. If the angle between the vectors is small, and when I say large, I mean close to 90. If it's far away from 90 and small, it's no good. And if it's far away from 90 and big, it's no good either. Yeah. So let's draw something. So this vector product was developed to model the moment of force. So let's consider a bolt and wrench. So let me try and do some drawings. So let's draw a normally threaded bolt. Now I don't know how to draw that, but just a normal one, righty tighty, lefty loosey. Maybe they should be going down, I don't know. And then the head of the bolt. Okay, something like this, right? Looking at it now, I've actually threaded it the wrong way, so let me just fix the thread. Yeah, so imagine doing righty tighty. Yeah, that's the way it should be threaded. Okay, and now what we'll do, so this is a bolt, and now we're going to draw a wrench on top of it. Now I'll do my best here. So the wrench will kind of encompass all that, and it'll go over here like this. Right, so you're looking at it from side on. This is the wrench. Now, how do you cause a moment in the bolt? Well, you apply a force somewhere on the wrench. So if I have a force here, color, that didn't come out to be a different color. You apply a force here. Now, the next question is, where is the force? So there is a central axis, a fulcrum, a place that the bolt rotates around. I don't know. What's the word? Fulcrum, anyway. I'm drawing a blank on the rest of it. So basically what you look at is you look at the vector that goes from the fulcrum, the pivot is the other word I'm looking at. From the pivot to where the force acts. So this is going to be, this vector here is going to be the displacement. And we've got the force vector. And if the force, the way, like you don't pull a wrench or push a wrench, that's like when I say pull, I mean, you don't do that. Let me see, let me use the right color. So you don't pull the wrench, you don't push the wrench, you go at an angle, hopefully of 90 degrees, if you want to cause a torque or a moment. Now looking at this one, the way I have it, isn't this lefty loosey? So it's going to rotate from the top in a anti-clockwise fashion. And so where the bolt goes is because we're saying that the vector product of these is a vector, it has to have a direction. And what I'm saying is the direction of this yoke is, running out of colors, the moment. So I'm going to use this Greek letter here for tau, and that is going to be equal to the displacement crossed with the force. So all I'm doing here really is I'm kind of describing the direction of the vector product. It kind of obeys righty-tighty, lefty-loosey. It could also be called the right-hand rule, which might be hard for me to explain here. I might draw something on the next page. Okay. So, and obviously if the force goes in the other direction, so it comes from the opposite direction, that will correspond to righty-tighty. The wrench will go in a clockwise motion if you're looking from the top, and the natural thread will mean the bolt will go down, and so the moment will be down. Now, of course, the problem is if you change the thread to unorthodox, the direction of the bolt is not the same as the direction of the moment. So the moment isn't really pushing it down. That's just a nice way of remembering it. So what have we got here? We have two vectors here. The force vector, which is applied at the position of the displacement vector. Yeah, we know the current righty-tighty, lefty-loosey, or the right-hand rule, the bolt here will go in the up direction. This is accounted for in the definition of the vector product. So, I'm gonna try and draw something. I'm a really bad drawer, but I'll do my best here. So, this is supposed to be a thumb of the right hand, and if you put your hand out, your fingers out, okay, it's not too bad. Got the right number of fingers and everything. So what you have here is your fingers point in the direction of you. Sorry, not you. Now, if you close your fingers as far as the vector v, yeah, so there's your hand, and then if you can, with your right hand, sweep with your fingers to the position of v, with your right hand. So here we go. You kind of close you kind of close your hand there. So U is going like that, and now your fingers pointing in the direction of V. And in that situation, in that context, the direction of U cross V will be in the same as your thumb. Now, if you swap U and V, if you need to sweep, or say if you want to do V cross U, for example, it doesn't work. You have to actually put your hand upside down. So if I show it the other way around, so if you want to do the other way around, V cross U, you'll have to put your hand upside down. Yeah, this is kind of hard to draw. I can't draw, like, that's the other thing. So that's your hand upside down, pointing in the direction of the vector V. So just put your own right hand in front of you, thumbs down, and then sweep to the position, sweep your fingers, kind of close your fingers until you get to U. Oh boy. I've kind of given up there now, haven't I? Yeah, this is a lot easier to explain in class. So U, V, so you sweep from V to U, then V cross U goes down. Yeah, if you're looking at those pictures, you'd be completely confused, and I wouldn't blame you. I'd say Google the right-hand rule. Okay, now it's not actually that important for us. I just want to explain the direction of it. There is one thing that is important here. We'll eventually show, you see these two blue vectors, U cross V and V cross U, they are going to be the same magnitude, but in completely opposite directions. So this is a terrible argument that V cross U is equal to minus U cross V. And that will be the case. So we'll look at this right-hand rule here in the context of the bolt. So the D, so put your thumb where the purple torque vector is, pointing upwards. Put your fingers out straight in the direction of D, and then sweep. So imagine the force vector actually being over here, and sweep your fingers from D to F, and you can do that with your right hand. So directly up in the direction of your thumb is the position of the direction of D cross F. Right. Now you don't have to remember all that because it'll all just come out in the maths anyway, but it is explaining things. Okay, so yeah, this is now I'm going to try and do a more traditional kind of a thing here. So if you've got, now hopefully you can kind of see what this is. So imagine this is kind of the floor. This might be, yeah, so both of these vectors you're imagining on the floor, or we're going to go back to something in a moment. Then by the right hand rule, this is the direction of U cross V. Whereas if you go the other way around, so both of them on the floor, V cross U goes down. Now what's arguably more important than the exact direction is that U cross V is perpendicular to both V and U. And V cross U is perpendicular to both V and U. That's far more important. So the cross product of U and V, it's perpendicular to U, and it's also perpendicular to V. And that's true also of V cross U. So I'm going to pause this and go back way earlier in the notes. So this is back on page 8, and this is me on the ground. And this is kind of showing it's showing two things. So both of my arms are on the ground in the directions of U and V. And what's actually this arrow here is the toilet roll holder. So there's a toilet roll holder that goes like this. You know, you put the toilet rolls on it, and that's going directly up. So if I do U cross V, and if you do your right hand rule, so if you can imagine your thumb and going straight up and your fingers outstretched to U and then sweep them to V, then that U cross V is up. And the important thing is that U cross V, it's going straight up out of the ground, it's perpendicular to U, and it's perpendicular to V. So there's a right angle here between U and V, and a right angle here, which I'll just draw over here, between U and U cross V. Okay, so that's what that picture was actually there for. Okay, now the next thing is saying that if you have if you have a vector, only the perpendicular part does any of the turning. So I'm not sure what I'm going to draw here. Let's see. So we'll do it with the door, I think. Yeah. So I'll actually draw a door here to make it make more sense. So let's have a door. So a door might look something like hinges. That's not bad for me for drawing now. Right. Now, if you're going to apply a force, say here, in an effort to close the door, not all of the force is going to cause any kind of a moment, because what you can do is you can decompose the force into a bit that is perpendicular to the door and a bit that's parallel to the door. So we have the parallel part parallel to the door and perpendicular to the door. Now the perpendicular part of the force will cause a moment about this displacement, but the parallel part of the force cannot turn the door. The parallel force is basically pulling the door along its own direction. It doesn't do anything. So all of the moment, and this is all I'm going to write here because I'm not exactly sure what I wanted to do here, only the part of the force that's perpendicular to this displacement does turning. That's probably not even English, but that's all I want to say. So what that means basically is that the moment associated with this is 0. And we can write down that the moment of the force, which is something you should know, distance by force, but it's only the distance between the hinge, the pivot, the fulcrum, and when the force acts, that's the distance, and law of the lever, whatever it is, and then the force. But that's only the case if they're perpendicular. But here I'm saying they are perpendicular. So the moment, excuse me, the magnitude of the torque here will be, as you know it, distance by force. Distance, but it won't be the magnitude of the force because some of the force is parallel and not doing any turning. It'll be that bit that is perpendicular. Now that'll all come out in the wash. So okay, let's go and write down a proper definition. So the vector product of u and v is a vector whose magnitude is given like this. So what we do here now is, if we look at, and I have to be careful, I have to be very careful. I'm going to have to draw some more pictures here. And maybe I'll draw them down the bottom. Yeah. So what I want to say is the following. Now, I'm going to talk about, so the inspiration is coming from forces and displacements and moments, but now we're going to go just abstract. So your view, and a vector v. Okay, and I'm going to put down the angle in between them. I'm going to call theta. Now, if I'm looking at the magnitude of the vector product between these, the only part that does anything is this bit here. That's a v. So v is a bit parallel to u that doesn't do anything in terms of moments. So that'd be v parallel. But v perpendicular does. And we're perpendicular. V perpendicular does. And what we want to say is that the magnitude, not the actual, now the vector product itself is a vector. We will learn eventually how to calculate it. But the magnitude of u cross v is going to be the length of u by the length of the part of v that's perpendicular to u. And what you can show with a bit of trigonometry is that the length of the bit perpendicular is the length of v times the sine of the angle. And it turns out when the angle between them is bigger than 180, oh, I think it still works. I don't think I have to change anything there, because sine of an angle bigger than 90 is still positive. Yeah, so that's what it is. Okay, so that's now so what we're eventually, okay, let's write this down. So the vector product of u and v is a vector whose magnitude is given by the magnitude of u cross v is equal to length of u, length of v, sine of the angle in between. Yes, and the direction is perpendicular to both u and v. Now that gives two options. So that's u and v. Imagine these are on the floor. There's two options. It could go down, it could go up. They're the only directions that are perpendicular to the floor. Down is perpendicular to the floor, and up, and it's the one in this case when you have it like this, up, if it's a right hand rule, it goes like this. So we've kind of described the direction, and we definitely described the magnitude, so that actually defines the vector product. Now what you want to be able to do is be able to calculate it, and we will get there in time. Okay, we're going to look at some properties of the vector product. So if the vectors are perpendicular, the magnitude of the vector product is the product of the magnitudes. If they're parallel, then the vector product is 0. So that's basically saying that you can't cause any moment by pulling the door or pushing the door. In particular, because the vector is parallel to itself, u cross product u is 0. The other one we said, we saw that earlier, because the angle between u and v is the same as the angle between v and u, the magnitudes of u and v, or u cross v and v cross u, are the same, but they're in the opposite direction, so one must be minus the other one. That's the third one. The fourth one is basically just saying that the cross product u and v is perpendicular to u and v. Then that was not so important. And then what is important is I cross j is k, j cross k is I, and k cross I is j. And that's linked to the question that was asked in the live lecture about who picks the coordinate system. And as long as you have a relationship between the x and the y that satisfies the right-hand rule, you're fine. Okay, so let's write these down. So if the vectors are perpendicular, let's look, then the angle between them is 90. And so the magnitude of u cross v, which isn't the same as u cross v, just the magnitude, is the magnitude of u times the magnitude of v times the sine of the angle in between. And if they're perpendicular, that angle is 90. And sine of 90 is 1. So we find that in this case, we get length of u, length of v by 1, which is just the length of u by the length of v. So that's basically your moment calculation, saying that the moment of a force is the force by the distance. That it only applies when the force and the distance are perpendicular. Otherwise, it's more complicated, and you need what we're doing in this chapter. If they're parallel, then the angle between them is 0. So if the vectors are parallel, let's just draw that just to convince you. Like if you put them, like there's no angle between them. If you draw them on top of each other, the angle is 0. So magnitude of u cross v is equal to magnitude of u times magnitude of v times sine of 0. And sine of 0 is 0. So you get length of u, length of v by 0. So what does that show? If vectors are parallel, their cross product is 0. And u is parallel to itself. So u cross u is 0. Then the next thing is arguing it out. So as the length of A is the same as the length of minus A, that means that the length of v minus u is the same as the length of v minus u. So that's just saying that if you got a vector there, say u, minus u is in the opposite direction, but it has the same length. And the angle between, if you have two vectors, say u and v, the angle between u and v is the same as the angle between v and u. So we have this kind of calculation that the length of u times v is equal length of u, length of v, sine of theta. I don't actually think we need that absolute value. It's just if the angle between them can't be negative, so don't need that absolute value anyway. So then you can just swap the v and the u because they're just numbers. And this is the length of v times u, which is the same as the length of minus v times u. So what we're saying here is that u times v and minus v times u have the same length. And then we say that these two are in opposite direction, and so it follows. So basically what I've said here is that I have a vector, say this is u cross v. And I have another vector v cross u. Now they're in opposite directions, and all we have to show to say that one is minus the other is to show that they have the same length, and that's what this calculation is doing. Okay. The fourth thing is saying that the dot product of u with u cross v is 0, and the dot product of v and u cross v is 0. So all that's saying is that u and v are perpendicular to the cross product. And what you should, so by definition, u cross v is perpendicular to both of them, and then just remember that two vectors are perpendicular to each other if and only if their dot product is 0. And so if u is perpendicular to u cross v, and if v is perpendicular to u cross v, which is the left-hand side of this, then the dot product of u cross v and u is 0, and the dot product of u cross v and v is 0. That's all that's saying. Okay, what the hell is this? Oh yeah, this is the thing about the parallelogram. Okay, so I think it's saying that, what are we saying? The magnitude of the vector product equal to the area of the parallelogram. Now this is related to the fact that you want to say that when the vectors have a big angle between them, the vector product, the cross product, is large. And so if the vectors have a big angle between them, the area of the parallelogram they make is quite big. Versus if you have, say, them kind of pulling together like this, or even more extremely, so you only get a tiny little parallelogram, and the area of this is quite small in comparison to if they were fully at 90 degrees with the same length. you get a bigger area. So it's just an expression of the fact that when the vectors have a big angle in the sense of close to 90, the vector product is a large magnitude. So I think, are we actually going to show this? Yeah, we will for the crack. So I think what I'm going to do is I'm going to drop a little perpendicular on this picture. And you can show that if this is theta, the angle between u and v, if you do a bit of, now maybe we'll just do it just to be clear. So in this little triangle, BAD, the sine of theta is the opposite, which I'm going to call this the length of the, well, let's call this h for height, is, now for height, not for hypotenuse. So it'll be the height over the hypotenuse. And the hypotenuse, the length of the hypotenuse is the length of the vector u. So if I multiply both sides by the length of u, this perpendicular height in this vector is equal to the length of u by sine of theta. And what that means is the area of a triangle being half the base by the height, and the base is the length of v. So the area of this triangle is half the base, which is length of v, by the perpendicular height, which is length of u by sine of theta, which we found. And that's the same as this thing. And if you double that, in other words, because these two triangles are exactly the same because they have all the same lengths, if you double this area, you get the area of the parallelogram, which is the same as the area of the, the magnitude of the cross product. And now what's the last thing we're looking at? Oh yeah, this is the best one, IJK. So draw your picture. So you can pick X, Y from the floor, but you have to, if you put X and Y in a certain way, Z has to go down. So the proper way to do it is, so imagine you're sitting in the classroom here. There you are, happy out. And there's the whiteboard or whatever. I won't draw me, but like, well, what am I doing? I'm drawing. Sorry, I'm just having a bit of crack there. You know, see what I'm doing. And so this is the whiteboard. And just look over at the wall here. So this is the corner of the room. Right, you look over the corner of the room here. The way that it's set up is that if this is the setup, this is X, this is Y, and this is Z. If you want to call this Y X instead of XY, then the Z has to go down because it messes up this IJK business. So let's draw our little IJKs. I, 1 in the X, J, 1 in the Y, K, 1 in the thing. And notice that if you take any pair of IJK, the other one is perpendicular to it. Like look at I and J, K is perpendicular to all of them. Look at K and J, I is perpendicular. Look at K and I, it works every way. Now the right hand rule, the easiest one is probably looking at I cross J. So if you sweep, you can do a right hand rule there with your thumb pointing up and sweep from I to J. So if you do I cross J, it's certainly in the direction of K. And all I really have to show here is that, we'll just do it with IJ, is that, so the length of I, the cross product, is equal to length of I times length of J times the sine of the angle in between. And of course, they're at right angles. So it's sine of 90. And sine of 90 is 1. And the length of I is 1. The length of J is to get 1 by 1 by 1, which is 1. So the magnitude of I cross J is 1. And it's perpendicular to I and J. So it's either up by 1 or down by 1. So it's either K or minus K. And the right hand rule says I cross J is equal to K. So here's this, you can actually see the sweep. There's the sweep. I cross J is equal to K. And similarly, you can show that J cross K has to be equal to I, and K cross I is equal to J. And what's important is the order of multiplication in terms of cross product is important, because if you do J cross I and you try and do your right hand rule, it doesn't quite work unless you point down. So I cross j is in the opposite direction to j cross I. Now there's some stuff there to help you visualize the vector product if you want to go into this applet there. Yeah. So I think we'll leave this a long enough lecture. What you have now, what you should have is just a feeling for the vector product. You get these two vectors, you combine them, you get something that's perpendicular to both of them. When the vectors are kind of pulling together, or pulling very, very far apart, this vector doesn't have a large magnitude. But when these vectors are like close to 90 degrees, it's very, very big. What we're going to do in the next lecture is find out actually how to calculate it in terms of your IJKs.